Last lesson we looked at some things that may have been a review of grade 9. And today we're going to look at a couple more that are kind of review of grade 9, although you might not have heard of them specifically referred to in the same way that I'm going to now. The first part, what we're looking at is a guy by the name of Kirchhoffs who came up with a set of rules or laws. They're probably better described as rules to describe how current and voltage and resistance operate in a circuit. And the first thing we need to understand before we get on to analyzing the circuits using Kirchhoffs laws is the different types of circuits that exist. So we're talking about the difference between series and parallel circuit. In a series circuit, if you remember from grade 9, that there's only one path for the charge to flow, for the electrons to move. And in parallel, there are multiple paths. So what this looks like in a simple series circuit with light bulbs might look something like this. So we've got 4 light bulbs all in one loop. So the electrons only have one choice of which to flow. Either the electrons are flowing and they're giving off energy, or they are not flowing and they're not giving off energy. In this case, a parallel circuit would look like something like this. This isn't a properly drawn circuit diagram. Get rid of that. This is a sketch. Sometimes when you're just trying to illustrate a point, a sketch can do just as much as a properly drawn circuit diagram. In a lab report, you would need to include a properly drawn circuit diagram with neatly drawn components and straight lines and whatnot. So some of the differences between a series and parallel circuit. If there is a break somewhere in the circuit, we'll say right there, there's a little break. So if there's a break, you will have no current flowing whatsoever. So a lot of people might look at it and say, okay, well, the electrons are coming out of the negative side of the battery right there, and they're going to flow until they hit they're going to flow around here until they hit the break, and then they can't go anymore. But remember, if there's a break, that means that they're not being pulled from this positive side, so there's no reason for the electrons to go anywhere. Therefore, they're not going to spend any energy trying to get through the light bulb, and the result is that the electrons don't flow whatsoever. None of the light bulbs stay on. Consider this like old Christmas lights, when all the lights were in a row, and when one light bulb would blow, all of the light bulbs would go out, and you'd have to replace them one by one in order to see which one was actually broken. Contrast that with a parallel circuit, and if there's a break, it really does depend on where the break is. So if the break is, say, here, then this light bulb wouldn't work because the electrons couldn't flow through there, but all the other bulbs, the electrons could flow through there. So the current, remember conventional current going from positive to negative, would come up there, go through there, and then come back. Or it could go through this branch of the parallel circuit. We call each kind of loop of a parallel circuit a branch. So the current may flow even if there's a break. In the circuit. Now, if we put the break in the circuit up here, we'll say, then there's no way for the electrons to move past that break. The electrons are not going to be attracted to the positive because they're not going to be able to get through that little break there, so we would get no flow whatsoever. The other implications of a series and parallel circuits we'll see when we start talking about Kirchhoffs laws. We can discuss that in class a little later. I did want to show you one other kind of type of circuit if you want to think about it in this way, and that is a combination circuit. A combination circuit is, well, exactly what it sounds like. It's a little bit of series and it's a little bit of parallel. They tend to be a little bit more complicated because we can't treat them as either just in series or just in parallel. They might look something like this. There's a resistor, here's another resistor, here's another resistor, and back, and that looks like a series circuit until I do this. And now we have a combination. This is obviously a parallel circuit because there's more than one path, but there are parts that are in series. So two components are in series when electrons can pass through each in one loop. Electrons or resistors are considered in parallel when the electrons have to make a choice. Now, this is not a conscious decision. Electrons don't have consciousness, as best we know. But the electron can only go through one or the other. So let's label these as 1, 2, 3, 4, and 5. So let's look at the combinations of resistors that are in series and the combination that are in parallel. So with resistor number 1, every single one of these resistors can have electrons pass through one and pass through all the rest of them, because either the current is going to flow this way, positive to negative, and it's going to go through number 1 and come back, which means it's gone through 2, 3, and 1. Or the current could flow this way, which means it's passed through 2, 4, 5, and then 1. So in 1, all the resistors are said to be connected in series with number 1. And the same thing for number 2. But let's look at number 3. So if we have resistor number 3 right here, and as we can see that for that first loop, the electrons will pass through 2 and 1. So it's in series with 2 and 1, but the electrons cannot, the charge cannot flow through 3 and 4 or 5. So they have to make a choice of which one to go through. And so they are in parallel. Number 3 is in parallel with 4 and 5. 4 is in parallel with 3, 3 is in parallel with 4, they're the same thing. The only other combination that we haven't looked at is 4 and 5, and 4 and 5 are in series with each other because the electrons must go through 4 if they are going to go through 5 and vice versa. So we can see this is why we have a combination. If you look at our series circuit up here, on the left, every single one of the light bulbs are in series with each other. On the right side, in parallel, every single one of the light bulbs are in parallel with each other. So it's a parallel circuit. And as you can see with our combination circuit, some are in series and some are in parallel. Which brings us to the idea of Kirchhoffs Laws. There are two laws, or Kirchhoffs rules, if you prefer that way. The first one is that the current entering a point in a circuit must be the same as the current leaving it. I like to think of this as a traffic analogy. The number of cars that go past a point in a road or go through an intersection, the number that go in have to be the same as the number that come out. If If for any reason those two numbers are different, you do not want to take that road. It is physically impossible. Even if the car gets in an accident and gets shattered to pieces, all of the pieces will eventually be removed. So the number of cars that go in is the same as the number of cars that come out. The number of electrons that go into a circuit is the same as the number of electrons that come out. And that kind of gets rid of the idea of electrons being consumed as they go through loads. Electrons don't get used up when they go through a light bulb. Another analogy would be to consider the electrons like people and the energy that the electrons carry to be like money. When you go to a store and you go through the cash and you want to change your money into something else like groceries. So you want to take the energy that is your money and you want to convert it into another form of energy, and that is food. You go into line, you present your food, you give the money, you give your energy. Now you don't cease to exist when you do this. You still are there, you just have less money now because you've converted that money into another form. So that's what happens. That's the basic premise behind Kirchhoffs' current law, the current going into a point. So if you had, if in an intersection, if you have 5 cars going into the intersection, you have to have 5 cars that come out. Kirchhoffs' voltage law obviously deals with voltage, and in any loop of a circuit, the voltage must be equal to the voltage out. You can think of it as conservation of energy. Conservation of energy. Because remember, voltage is the amount of energy per unit charge. So at any one particular loop, the energy that you gain per unit of charge in the battery, most likely, or other power source, has to be equal to the energy that you lose in that loop. You can't store up energy to be used later. Think of it like maybe like a ski hill. The energy that you gain in going up the ski lift, you have to lose to get back down to the bottom of the ski hill. You can't save up some of that energy for later. It's not like you can just save up a little bit each time and the ski hill is going to lift you higher and higher each time. You're always going to start off at the same point, end up at the same point. So let's see how this goes into practice. And we'll look at an example over here. So on the left, I have a circuit. I'll have a source up here, and it is a 12-volt source. I have resistor 1, which according to my little table has a resistance of 12 ohms. Resistor 2 has a resistance of 30 ohms. Resistor 3 is 15 ohms. Resistor 4 is 5 ohms. Those are the things that you're given. And I've given you one other piece of information that eventually you won't need to do after we look at tomorrow's lesson. I wouldn't need to give you this. But for right now, I will also tell you that the current going through resistor 1 is 0.5 amps. So I like to organize this. This is kind of our first step towards what we call circuit analysis. I like to organize this in a little bit of a table, and you can see what my table looks like over here. So let's go through the steps. Really, we have 3 laws or rules in which we can use right now. We have both of Kirchhoffs' laws, Kirchhoffs' current and voltage laws. We also have Ohm's law which we can use. So Ohm's law is probably the easiest one to start off with. So if I look right over here, I can use Ohm's law knowing that R is equal to V over I, or V is equal to I times R. So in this case, because I'm given the current through the first...
801, please. $10, 801.
And this is why I usually do the lessons in the evening when everybody's gone home. The first resistor is what I'm worried about, and I have the current through the first resistor, so I'll call that I1, and I have the resistance of the first resistor, I'll call that R1, which really means that this is the voltage going across the first resistor, V1. And so I can plug in my numbers. 1/2 of 12 gives me a grand total of 6 volts. So let's call that stage 1. I'll put a little 1 up there so you can follow along and see what order we did this, and that is 6 volts. So there's Ohm's law being used to get part of it. Now, what else can we do over here? Well, we can look at Kirchhoffs' voltage law. I'm going to change colors here, and let's use, for number 2, let's use Kirchhoffs voltage law. This is a lot like doing a puzzle, and you can't just throw pieces together and make them fit. There is a particular order that is easiest to do things, and in this case, there's a particular order that's the only way to do things. Now, this isn't the only way. There isn't something else that we could have done, but let's just focus on this, on number 2 for right now. Now, if we use Kirchhoffs voltage law, Kirchhoffs voltage law says any one loop has the same voltage out as the voltage in. Well, the voltage in is the 12 volts in the battery. So if we look at this loop right here, we gain 12 volts. We know based on our last calculation that we lose 6, and then we're going to start coming back. Okay, so voltage in is the 6 volts in the battery. Voltage out is the voltage through 1 plus the voltage through 2. Therefore, oh sorry, that's 12 volts in the battery. Thanks for pointing that out. So 12 volts is equal to the 6 volts that we calculated V1 plus V2. So therefore, V2 must be equal to 6 volts. So that's the second part. Now, that fact that those are both 6 is kind of a coincidence. I mean, it turned out that's just the way it needed to turn out, but those are not always going to be equal. So that's one thing that we could have done. Let's look at another step 2, and I call it another step 2 because it could have been done, actually we could even call it another step 1, I suppose, because it could have been done first, and that's using Kirchhoffs current law. Kirchhoffs current law says that the voltage into a junction or into a point is equal to the voltage out. So if we go back and we look here, there is 0.5 amps that is coming into the into resistor 1. So according to that, it must mean, since there's nowhere for it to split anywhere in between our source and R1, it must mean that if 0.5 amps is going through there, then you must have 0.5 amps coming through there. Or in other words, the current coming out of the source must be the same as the current going through 1, because there's nowhere else for it to go. So the current has to stay the same at every point. There's nowhere where it splits. And so the current coming out of the source has to be equal to 0.5 amps. So we'll call that another 1, because that could have been done first as well. Which means that we could have, we'll use black here, let's go back to, well, we'll leave it as red actually. We could have, as the second part, used Ohm's law again, R is equal to V over I. And so in this case, it's the resistance of the source, or in other words, the total resistance in the entire circuit, and we're going to get into this in more detail in the next lesson, is equal to the voltage across the source divided by the current through the source. So 12 divided by 0.5 gives you 24 ohms. So there's 24 ohms of resistance in total in this entire circuit. Right? And you'll notice that if you add up all the resistances, it doesn't seem to work out that way, and we'll look at why that is in the next lesson. But there are a bunch of things that we still have not calculated that we could go ahead and do. One of those things over here, or draw this in green, in step 3, we can say that I is equal to V over R. That's Ohm's law being rearranged. And so that's I2, that's our second resistor, is equal to V2 over R2. V2 was 6 volts. R2 is 30 volts. I'm sure there's some of you who are making a lame Star Wars joke out of that. No, maybe it's not that lame. 0.2 amps. So in step 3, we can figure out that the current going through resistor 2 is 0.2 amps. Which brings us back to Kirchhoffs current law. So we know Kirchhoffs current law. We know that go back up here, there is 0.5 amps coming into that junction. We just calculated that we had 0.2 amps coming out that way, so we have to have a certain amount coming out that way. So I1, the current coming out of I1, that's the current going in. The current coming out is going through I2 plus the current going through I3. So 0.5 amps is equal to 0.2 amps plus I3, which means I3 is equal to 0.3 amps. You'll also note that the current going through 3 has to be the same as the current going through 4 because there's no place for it to split up. That's also part of Kirchhoffs law, so we can say that's equal to I4 as well. Excuse me. So we can look at that as step 4, and that is 0.3, and that is also 0.3. From there, we can use Ohm's law in step 5. V3 is equal to I3 times R3. So 0.3 times 15 gives you 4.5 volts. Similarly, V4 is equal to I4 times R4, and that would give you 1.5 volts when you plugged in those numbers. So if we head back up to our chart, in step 5, we get 4.5 volts and 1.5 volts. The great thing with these is that you can check your answers, because there should always be two, I shouldn't say always, but most of the time there's going to be two different ways of calculating that last value. Once we knew this should be a foregone conclusion, because we can use Kirchhoffs voltage law again. So let's check. If this works, then Kirchhoffs voltage law should work as well. So what do we have? In one loop, the voltage in is 12 volts still. And if we look at the large loop going all the way around here, then the voltage out is V1 plus V4, sorry, V3. V1 plus V3 plus V4. And so 12 equals 6 plus 4.5 plus V4, and when you calculate V4, you get 1.5 volts. So the fact that those are identical doesn't prove that you're right, but it definitely leads to you being a little bit more certain. And so we started off with only the numbers in black, and all the numbers in blue, green, and red we were able to calculate using only Kirchhoff's two laws, as well as the resistance formula, Ohm's law. So there are lots of really good questions on this. We're going to add one component to it in the next lesson, and look at a whole bunch of different examples. There's lots of stuff in your textbook and your hit list, so make sure to go ahead and do that, and we'll look at some more examples on top of that in class.